Good afternoon, everybody, and thank you for being here. As such, okay. Let me close. Today we will talk about Radiotracer and so tracer technology with Professor Tor Bjørnstad. Let me say a few words about the speaker of the day. So Professor has a doctoral degree in nuclear chemistry and is a professor in radiochemistry, and he is involved in radiation sorry, there are other people in the waiting room. He has been involved in the tracer technology field since 1987. Of course, he worked in various nuclear R&D institutions previous to be professors, and since 1987 he's started work as head of the section for tracer technology at the Institute for Energy Technology in Norway, mainly working with the petroleum and the industry-related problems. So he's a very experienced person in this field, and in 1995 was appointed as principal scientist and head of the department for reservoir and exploration technology at the same institute. And now he's a professor emeritus in nuclear chemistry and nuclear physics at the University of Oslo. So I would like to thank you, Professor Bjørnstad, for accepting our invitation to hold this webinar on this topic. And I leave the floor to you for your presentation. Thank you.
Thank you very much, Elena. And welcome everybody. I hope you sit back in your chair, maybe with a cup of coffee or a cup of tea. In fact, I have brewed a cup of tea myself. So I invite you to join me on this very brief journey through part of the of the nuclear technology that we call radiotracers. In fact, I have named the presentation today radiotracers, the singing detectives, and it might become clear for you as we go along why I have said the singing detectives. So why don't we start right on? I suppose now that most of you have some basic knowledge of radiochemistry and the properties of radioactive nuclei, so I have not spent time, I will not spend time on going in details, unless except from a couple of slides in the very beginning. So we say that the emission of particles or electromagnetic quanta from the atomic nucleus, that we call radioactivity. The emitted radiation is normally and most of the time high energetic, and it interacts with matter, which is very important. This is the basis for detection of the radiation and also for the practical use of the radionuclides. So we have sort of a nucleus, and it emits different types of radiation, alpha particles, for instance, which is a helium nucleus. It emits beta particles, which are of two kinds. We have positively charged, which we call positrons, and we have negatively charged, which we call negatrons. And we have gamma radiation, which is electromagnetic radiation. So that this, of course, you knew beforehand. But this is just like an introduction to things. Now, then all the radioactive nuclei that we know have been plotted into a scheme like this. We have neutron number on the x-axis and proton number on the z-axis. So each proton number defines the chemical element, you might say. Very far down here, we find carbon. In the middle, we find iodine, and on the very top, we find uranium. And all the others are have their own place in this scheme. The black squares are the stable nuclides. The red ones are those that emits beta plus particles, or it decays by electron capture decay, and I will not elaborate further on what that is. So we have the blue, which is those decaying by beta minus particles, yellow by alpha decay, and the green ones with spontaneous emission. This chart is called the chart on nuclides, or if you like, the nuclear chart. And to me, it's kind of the world chart. It's everything we have. All the blacks is everything we have. It's everything we are built up of. But we are mostly interested now in the colors. Now, we are going to use radionuclides as tracers, radio tracers, or as radioactive labels on tracers. And in this situation, I have to define two different types of tracers. One is called the passive tracer, and the other one is called an active tracer. We start with the passive tracer. A passive tracer, also sometimes imprecisely, or I would say wrongly, called ideal tracer, is a specific and easily detectable substance. It can be a gas, liquid, or solid, which is introduced in very, very small quantities into a process mass flow in order to follow the mass flow development and study the process mechanisms. It's a long sentence, and maybe you have to read it twice in order to get everything here. It is very important, though, that in this case, the tracer itself must not perturb or disturb the process or the traced medium in any way, meaning that the medium itself or the process itself does not know that the tracer is there. Nor must the process perturb the tracer behavior different from the medium to be traced. So it is passive in all respects. It's participating in things, and it is reporting back to us what it has been participating in. And so we can understand the process flow. So that was the passive tracer. Then we have something we call active tracer. So this is the definition of an active tracer. An active tracer, also sometimes, and rightly, I would say, called reacting tracer, is a specific and easily detectable substance. It can be a gas, liquid, or solid, which is introduced in small quantities into a process in order to study certain defined properties of the process. Not to, as for the passive tracer, to understand the flow structure, but to study defined properties of the process. Important now is the tracer must interact with the medium, the process, or with the surrounding media in qualitatively and quantitatively predictable ways. And that is different from the passive tracer, which we said must not interact. This one must interact. And the degree and extent of the interaction is a measure of the wanted properties. I will give, later on, I will give some example of this, so it might become a little bit clearer what is the meaning. Now, tracers can be radioactive or non-radioactive. The non-radioactive tracers, most of the time, they have a detection limit which is not that very, very low, meaning that we have to use much more tracer in order to do that. And it is not low because they have to be provoked in order for us to understand that they are present. So here, for instance, we have tracer compounds, which I sort of now irradiate by some laser light maybe. And during irradiation, some of them, only a few response. And those are the ones that we can see. We don't see all the others which are there. That's why we have to use much more tracer. The non-radioactive tracer concentration is analyzed by using an external perturbation whereby only a small fraction of the tracer compound responds. Now, unlike the radioactive tracer, here I say the radioactive tracer, they are expressing themselves. They don't need a provocation. Yeah, okay, I go back. So what you see here is they emit radiation, and in this case, they emit gamma radiation, which is a frequency spectrum. And you see, I played a tune here, and as soon as we hear this tune, you recognize it. Oh, this one there, it is, do you know what it means to miss New Orleans? And there is no other tune like that one. And like here, when I see this frequency spectrum, which is the gamma radiation spectrum, I can see this one there is the spectrum of cobalt-60, and there is no other radionuclide with that one. So when I label my tracer with cobalt-60, I have made a radio tracer that is recognizable in one special way. And you see the two peaks here. And just to explain you the two peaks, we have here an energy axis upwards, so increasing energy upwards, you might say. And on top there, we have somewhere placed on that axis, we have cobalt-60, which is the radioactive label in this case. Long half-life, 5.2 years. It decays by emission of beta particles to excited levels in the daughter nucleus. And to this level, for instance, most of it decays to that level, 99.88% to that level, and a small fraction to another level. Now, when the nickel, which is the daughter product, and also stable, it's stable in the ground state, is excited, it wants to de-excite, and it does so by emission of gamma radiation. And this gamma radiation is so-called coincident because the lifetime of the excited level is very small, picoseconds. And this is the expression we saw on the previous spectrum. So what we measure is the spectrum. It is because the spectrum is because of the coincident gamma radiation like this, and it produces two peaks, recognizable. We know it. Now, most of the time, in order not to contaminate anything, because we are talking radioactivity here, we shouldn't do any radioactive contamination anywhere. So we should strive to use short-lived radioactive tracers. That means the radionuclide, which is either the tracer itself or the label on the tracer, should be short-lived. And especially it is important that if we are using this at remote locations, we cannot use long-lived anywhere, and especially in remote locations. Short-lived radio tracers in process industry. Why and how? Short-lived gamma emitters allow for monitoring details on mass flow in non-transparent pipelines, reaction vessels, and other process equipment. It is because it emits gamma radiation. We're mostly interested in those emitting gamma radiation. It emits gamma radiation, and that has a very strong penetrating power. It penetrates through a rather thick, let's say, steel walls, in pipelines, and so on. So we don't need to introduce any measuring equipment inside. We measure everything from outside. We put our detector outside the pipeline. So that's very interesting. That cannot be done with non-radioactive tracers, for instance. The non-destructive, continuous, and online monitoring is possible. We can monitor continuously in this way. We don't worry about radioactive waste in the processed material because it dies away. It's short-lived. It dies away and leave no trace. And this can best be achieved by so-called tailor-made radio tracer generators. And what this is will become clear in a moment. I have to start by defining what a radionuclide generator is. So a definition here. A radionuclide generator is a chemical, physical, or mechanical device that is based on a nuclear mother-daughter genetic relationship. And it allows for chemical and or physical separation and extraction of the short-lived daughter from the long-lived mother, and can be operated in a repeatable fashion. I will, this become clearer after a few slides now. So again, we have the energy content upwards. We have the mother nuclide up here, which is radioactive. Now it wants to get rid of some of its excitation energy by emitting radiation. So it emits radiation and produces a daughter. The daughter itself is lower on the energy axis. That might also be radioactive, and it produces a granddaughter, and so on. And we call this mother-daughter a nuclear genetic relationship, or the mother-daughter-granddaughter nuclear genetic relationship. So a radio tracer generator is based on that. But not only, not only that. I will come back a little bit to that later. So the long-lived mother, we need a long-lived mother. It has to be relatively long-lived. Is fixed on a, let's say, an ion exchange column support. And okay, so it's fixed there. And then it gives birth to babies all the time. Decay products, daughter products all the time. The daughter products, of course, they are different from the mother when it comes to chemistry, because it's a different chemical element. So maybe that is not very much fixed. It's not so strongly fixed on the support. So it can be removed from the column without removing the mother. So what happens is that we can remove the daughter product and leave the mother. And as soon as we have removed the daughter products, the mother continues to produce daughters that we can remove in the next time, and so on, in repeatable fashion. These daughters may be tracers directly or not. They may be labels that we have to produce tracers from this by complexing them with some organic complexing agent. There are different types of interesting mother-daughter relationships that is the basis for the generators, which is, and this especially here, and there are several more, but these are just examples that we can use in industry and even in medicine. But we have to produce a tracer. And so we say we have something we call a radio tracer generator, RTG generator. Definition: a radio tracer generator is a chemical, physical, or mechanical device which is based on a radionuclide generator. It contains possibly additional features like labeling chemistry in kits that can be automatically or semi-automatically operated to produce proper tracer compounds of the daughter compound separated from the generator. And that can be done for gaseous, liquid, or solid phases. So we produce tracers for gas phases, for liquid phases, or for solid phases. And the principle is the following. We have the mother radionuclide fixed on a column support, giving birth to babies. Then we have to use, in order to remove that one and produce a tracer directly, we have to use some special elution agents here, maybe containing a complexing agent. We might adjust salinity here, pH, and so on. And the aqueous solution and the complex daughter possibly might be extractable into an organic phase. So we can produce either an aqueous tracer or an organic phase tracer. So we just inject the complexing agent along with the elution agent here. It goes down, fixes onto grip on the red ones, and out comes the ready complex tracer. This is the tracing compound, and this device we call a radio tracer generator. There are examples of that. I will not go into it. I thought that could be sufficient as an introduction of tracer and radio tracers. And now I would like to show some practical examples. Now, this event here is scheduled to take around 1 hour, and we'll see as we go along if we can achieve all of what I wanted to say. But we start here. And we start with the practical example 1, that is radio tracer oil reservoir examination by radio tracer injection. An oil reservoir and the knowledge of the oil reservoir, we have that from seismic examinations and from drilling of wells. And you see all the bars here, there are wells drilled in a geological setting, a geological reservoir. We know exactly how the reservoir is looking like at the spots where we have drilled, but we don't know very much in between the wells. So in between the wells, all knowledge is based on interpolations, which can be fairly well, but it can also be very wrong. And we don't know anything about the fluid movement in the reservoir. And in order to know something about the fluid movement, we need to, or we can use tracer compounds, and not least radio tracer compounds. So during oil production, most of the time, one injects water in order to push the oil to the production wells. And when we are injecting water, we inject alongside a radio tracer, which is dissolvable and a passively dissolvable in the water phase. So it does not interact with anything else than the water itself. So we just inject somewhere and see in which production wells the tracer is appearing, and at which time, and at which condition and content and concentration. All right, now we have to, in order to select a tracer that is possible to use in this case, we have to be aware that oil reservoirs are mainly composed or based in sandstones or in chalk rock. And for instance, here is sandstone, and the sandstone has a net negative charge on the surface of the rock. So we have here a picture where we have a flowing pore in the sandstone, pore, and a picture where we have also what we call dead end pore, which is not taking part in the percolation itself. It's just accessible through molecular diffusion. If I choose now a non-charged tracer molecule, what is the behavior of a non-charged tracer molecule? So let me see how it behaves. It goes there, it goes in the pore, it moves with the water, it diffuses out and back again in the flooding pore. So it is probing all the water volume correctly. What happens if I use a positively charged tracer? Okay, now it feels attraction to the surface. So it sort of tends to cling to the surface and be delayed. And it is now diffusing out and into the main flooding channel, but at a later time. It takes longer. What happens if I use a negatively charged? Okay, it feels repellation. It didn't go into the volume, into the dead end volume at all. And meaning that it moves faster through the reservoir. So, and this we have to know and have to define in order to select a good reservoir tracer. Now, here we see a situation where we have oil platforms, we have injection well and a production well, and we have a stratified reservoir, and we don't know exactly what it looks like in between here. So that's why we inject tracer. We inject a tracer, and it goes down the well, spread itself through and moves through different portions of the reservoir and come back to the reservoir, to the production well, where we measure the concentration. Now you see they had different delays here. One was moving faster than the other one, and so on. And what we produce is a relatively structured curve like this. Now, when we have something like that, that can be decomposed in different parts, like here, and that is indicative of permeability stratification of three different stratified positions here, where one stratification has higher permeability than the other one, which has higher permeability than the third one. And so this is kind of information that we can extract from this kind of experiments. So what we can back out is the preferential flow directions between wells. We can look at horizontal and vertical communication between wells, which wells are communicating. We can look at permeability stratification, what is the most permeable strata, and so on. We can look at sweep volumes, how effective is our injection of water in order to push oil to the production wells. And we can look at hard, large-scale heterogeneities like barriers to flow or fractures, and fractures, of course, the tracer will move very fast. A typical radioactive water tracer is radioactive water itself, because it does what water does and nothing else. HTO, tritium, here, HTO. Now, after we have injected water for some time and produced most of the movable, so-called movable oil, there can be very much oil left in the reservoir, which cannot be produced by normal water injection. And the oil companies want to know how much oil is there left. And this is the case where we can use a so-called active tracer. And the active tracer here is a water oil partitioning tracer. Now we want to produce and develop a tracer that partition between movable water and stationary stagnant oil. And so we say a passive tracer moves only with the water. Phase partitioning tracer distributes between water and oil. At residual oil saturation, water moves and oil is close to stagnant. So we develop in the laboratory sort of these tracers. We have a water phase and we have an oil phase, and we have different types of tracer. We have the passive water tracer and we have the partitioning tracer. And we shake the oil and water in a test tube, and let it come to equilibrium and measure then the concentration after equilibrium has been attained. So we measure the concentration of tracers, of the two types of tracers, in the two phases. And we see that for the passive water tracer, this stays only in the water phase, while the partitioning tracer has partitioned between oil and water. And if we say that we do the experiment at constant temperature, constant salinity, a constant pH, then we produce what we call a partition coefficient, which is a physical constant, which is the concentration of tracer in the oil phase to concentration of tracer in the water phase of the green tracer. So this is something that we use in order to develop and measure remaining oil saturation in the oil reservoir. Now, here is a cartoon of a typical, let's say, sandstone. Let's say, so we have sandstone grains here, and there is an oil layer. The orange here is an oil layer on outside the sandstone grains. So it's an oil wet sandstone, this, and the blue is flowing water. So first we inject a water tracer. It moves without looking at the oil at all. It moves only in the water phase through the reservoir. So we can detect that. But if we inject a passive water tracer and an oil water partitioning tracer at the same time, this happens. You see, the red is moving only with the water, while the green one stays parts of its time in the stagnant oil phase. So it means that it is lagged behind. It is lagged behind. And the time difference there, the time difference between the aqueous passive water tracer and the partitioning tracer is proportional to the remaining oil saturation in the reservoir. And this can be backed out with a very simple, in the simplest case, with a very simple formula like this, which I'm not going to explain because of time. And I don't think I will not spend time on that, so I will jump over this one very fast. I will take practical example number 2, flow rate determination. Flow rate in pipelines, for instance, and flow rate measurements are used in physical metering, for instance. So it is very important to be able to carry out flow rate correctly. This can be done by using radio tracers injected. So we have a pipeline here, and it can be thick iron walls here. It doesn't matter for us because we have gamma emitting radio tracers that just penetrates the wall. And here we have a radio tracer generator producing short-lived radio tracers. So what we see here is a radio tracer. And upstream and downstream, in two positions downstream, the injection, we have a gamma detector here and a gamma detector there. So we inject the tracer as a pulse, and we measure the time it takes between the two detectors. And we see the first signal and the last signal. And the distance between what we call the first moments of the curve is indicative, or is a direct measure of the flow rate here, because now we know also flow rate, that means a linear flow rate or mass flow rate. We know the diameter of the tube, we can measure the mass flow rate. This is just something that, so it's used in oil production, for instance, but I'm not going to explain what this is. What we do not want for the tracer is the following situation. So we have the tracer injection, and when it moves along, some of it is lost because maybe sorption to the walls and so on. Then it is, in this situation, it is not longer a passive water tracer, and we cannot use it in this situation. Yeah. I think I skip that as well and go to practical example number 3. That is the residence time distribution and flow structure determination, and most of that is, let's say, used in chemical process systems. So we have injection of reactants here, different reactants in a reaction chamber. They should react with each other and stay there for a certain time in order to optimize the yield. It goes from the reaction chamber into a, let's say, a heating position. So it is heated to a certain degree temperature at a certain time, so that we optimize the yield when it comes out here. So, and you see, we have instrumented this system with detectors. So 2 detectors at this position, 2 detectors at that position, and 2 detectors at that position. The number of detectors, that's optional. That can be different. Now we inject the reactants. So they go in there, they react, and they move further on into the heating position, and they move out. But we don't know exactly if the system is optimized. In order to optimize the volume or the delay time in here and the optimum delay time in here, we have to look at the flow structure. And in order to understand the flow structure, we inject a tracer. And we measure the tracer as they pass through the detectors. And in the end, we construct curves like this. So this is for the first couple of detectors. That is for the second one. And this is for the third one. And then it seems complicated now, but we have underlying mathematical models where we can use these curves and back out what we call a flow structure of the system. Like this. Seems very complicated. I'm not going to explain what the different things here is. But when we see this structure, we can say that, oh, it's too much of that one. Oh, it's too little of this one. So we have to modify the outline or the layout of the reaction chamber in order for maximum yield to be produced. Practical example number 4. And then we use not liquid tracers anymore. Here, in this case here, I show here, we use particle tracers. So we have a silo here, and particles are moving down the silo, and we want to know the mathematical or the structure of moving of the particles through the silo. This is instrumented with 2 detectors. One detector here that can move this way, and the other one here that can move this way. That means they are on the same level all the time, and they move to optimize the readout or the activity detection level or limit level here. At each position, the radioactive particle is when the radioactive particle is moving down. So like this, radioactive particle moves down and the detector moves as well. So we are recording the movement of the detectors. In addition, when the particle is here, the detector is possible to change the angle between the detectors, and we record the angle at the same time. So when the particle is there is a long, relatively wide angle here. When the particle is on the other side, it's a more narrow angle. So we record the angle. In this way, afterwards, we have been recording the position, the vertical position and the angle. We can reconstruct the path of the particle. And when this is many times, and then we can construct a model for movement of particles in the silo. Now, this method can also be used in flooding systems, but I will not show it here. Practical example number 5. Yeah, mineral exploitation and separation by hydrometallurgy. It is nowadays we have many electrical instruments. We have electrical cars. We have many things that require precious metals, a lot of precious metals, rare earth metals, and so on. Where do we get that from? We get it from the rocks. And then we have to do mining, and we have to do separation of what we have found in the mines, and many of the separation, or part of the separation method, is what we call hydrometallurgy. So, and one of the most used methods in hydrometallurgy for separation of different compounds, when I say compounds, I mean in this case, I mean chemical elements. That is liquid extraction. So what we have to start with is, let's say we have an aqueous solution of some kind with different methods. Here I have shown 2 different methods. We are only interested in the green ones. We are not interested in yellow, in the red ones. So what we do then is that we inject here organic liquid with a complexing agent for the green, And when we have sufficient organic liquid, then we smash the organic liquid and the aqueous liquid together very fast, like this. So, and then in this process, we extract the green from the aqueous phase, and we end up with all the greens in the organic phase. So now we have separated the wanted chemical element from the unwanted in this way. Of course, in industry, we don't use separatory funnels like this. We do it in the laboratory maybe, but not in the industry. So in the industry, we have much more sophisticated methods. I will just show you. So we are again on extraction between and partitioning between aqueous phase and organic phase, because the partition coefficient is very important here. We should have as high partition coefficient as possible. Now we might have a more industrial system looking like this. We have a feed, a leaching activity. So we have a leach solution that goes down and is contacted with organic liquid here, while the remaining leach solution goes back to the beginning. So it turns forward and backwards here. And okay, so something is then extracted into the organic phase, and the organic phase is now again contacted with the aqueous phase. Something is stripped back to the aqueous phase, but some is not stripped back and goes this way. And finally, we end up with a product here in the end. And out here, we have the contaminants moving. So let's see now what happens when we have a green wanted chemical element and some other unwanted chemical elements going into this system together. So they go in together, they move through the system, extracted, stripped, contaminants are going up, and the final product is going this way. And the number of elements here can vary. The number of units can be varied, so there can be many extraction and stripping units as in a system like this. And here we have what we want. Then the tracer, we use a tracer for each of these contaminants, an elemental tracer for each of these contaminants, and an elemental tracer, radioactive tracer, radio tracer for the wanted element here. And then so we can optimize the chemistry in a system like this, in this way. Yeah, practical example number 6. yeah, in my reading of the time, I think we have we might have 15 minutes left or something like that. 15 minutes, 15, 20 minutes left. Practical example number 6. I have chosen one civil or two civil engineering applications here. First, leak detection, and secondly, sediment transport. Let's first look at the leak detection. Now, in civil engineering, there are many pipelines that is deeply buried. They can be pipeline for water transport. It can be pipelines for oil or gas transport, and so on, sludge transport, and so on. And the distance can be very long, many, many kilometers, buried deeply underground. Sometimes leaks develop, and it is often very difficult to find exactly where the leaks are. Now, if we have a situation where it is possible to load, there is an entrance port and an exit port at a certain distance, and also the distance between the entrance and the exit port can be several kilometers. But these ports are existing. Then we can sort of close the main pipeline so that it operates only between the one injection and emission port here, exit port. So we can inject a slug or a slug of a radio tracer. Let's do that. We develop a slug of a radio tracer. When it passes somewhere, the leak is, it will leak something into the ground. If we, during this operation, see that the leakage, that the activity or the total activity, integrated activity of the one we injected is higher than the one we end up with on the exit port. That means that this one, the integral of that curve is lower than that one. There is a leak somewhere between the entrance and the exit port, but we don't know exactly where. But then we have a trick. We inject here, or we lower what we call a pig. It is an instrumented pig containing a detector for radioactivity, for gamma radiation. It also has a positioning ability, so it knows where it is at any time. So we let it run through the pipeline here, and when it passes the pipeline, there is a detector response, which is read off. So now we know exactly where the leak is, and we can dig here to repair it and not dig up all the several kilometers between. So we can dig exactly there. This is one example of the use of radio tracers in civil engineering. Sediment transport. Waves erode coastlines. You see, it can be nice with waves because you can have surfing like this. Some people like surfing, but at the same time, coastlines are eroded, and we have problems with sediments that falls down to the bottom here. Problems with ships transport that cannot go into the harbor anymore because it is too shallow water, and so on. And what is the dynamics? What is the dynamics of the sediment? In order to understand the dynamics of the sediment, we can use a radio tracer. And then it is also most of the time particle radio tracers. Radio tracers made in the sand itself. So if we say we inject here a portion of sand, and look at we will look at what happens as a function of time. So at time t1 and t2, you see t3 and t4, it moves outwards like this. And then if we can measure where it is and the concentration, we can have a model for the sediment transport. And that we do in this way. So we have the tracer and we have a boat towing a sledge with a radioactive or a detector looking at the radioactivity emitted from the tracer itself. And in this way, we can reproduce the development and the movement of the sediment, you see. And then from this, we can develop a model for the movement of sediments. And we might then find that, okay, now it's time for dredging. We need dredging at this point to remove sediments, and we can dump it at this point, at another point. Yeah. Radioactive tracers in medicine. This has become a very important, and has been for many years now, a very important field of use of radio tracers. Now, maybe now more than ever, because of new methods, new detection methods, new tracing methods, and so on. There are mainly two types of measurements I would like to just mention here briefly. There's one examination we call SPECT, which stands for Single Photon Emission Computed Tomography, which requires that we have a radio tracer which emits ideally one gamma ray of ideally not too long half-life. That's okay. This one is okay. With an energy not very high. Optimum energy is 140, 150 kilo electron volts. That we have in this mother-daughter nuclear relationship. Molybdenum 99 goes to technetium 99M. That decays by 6 hours half-life down to the ground state, which has a long, very long half-life, so it's nearly, we can regard it as stable. And this emission is used in SPECT. There are several others that I will not mention here, but this is what we call the working horse in SPECT examinations. That is together with a gamma camera. So if we have a patient down here in the panel to the left, we have a patient here. We have injected a tracer containing 99M technetium into his body. It's distributing, and maybe we have designed that it should be distributed into and accumulate in tissue containing cancer tissue. So tumors, it should concentrate in tumors. Now, after some time, we use the gamma camera that consists of a detector, sodium iodide detector, a big one. And in front of the detector, we have what we call a collimator. So it's a lead collimator with holes in. So only the gamma rays coming in parallel with the holes can be detected. So we accumulate the spectrum for some time, and then we can see from this machinery, we can back out the distribution of the activity within the body. So we can see where the tumor is. If that was stationary, we would only have a projection, but it is not stationary. It can be moved around the patient. And this is an example of a gamma camera picture, SPECT gamma camera picture of the head region of an unfortunate patient. And we can see the patient with cancer in the throat and in the forehead. So the cancer accumulations here. And the instrument is like this. So this is the gamma camera itself that can be moved around the patient. And at each position it moves around, there is a new picture taken, and then we can reconstruct a three-dimensional picture of the cancer. I briefly mentioned in the beginning that we have two forms of electrons. We have negatrons, negative electrons, and we have positive electrons. These two electrons are antiparticles to each other. And we have fluorine, for instance, here we have a radionuclide called fluorine-18. It is a beta plus emitter. It emits beta plus particles. When the beta plus particles meet an electron, they both disappear. And two photons are produced in this way. And the two photons here, they are equivalent to the mass of one electron. So 511 keV, it shows up in the gamma ray spectrum, although it's not a gamma ray. It is a photon, it's not a gamma ray. Now, and another thing with these two, they are in coincidence, it's happened at the same time. And another thing is that they are emitted with 180 degrees to each other. This fact is used in what we call positron emission tomography. A typical instrument for positron emission tomography is here. We have a ring of detectors around here, and maybe he sticks his head in here, and we measure what happens in his head when we have given him what we call glucose, a sugar, fluorinating FDG, which is a sugar. So the reaction turnover rate in the brain of a healthy patient and at a patient with Alzheimer's disease is given in the panel to the left. We see to the far left, we have the normal patient with the turnover of sugar, the spending of sugar in the brain at the normal patient, and the spend over sugar in also an unfortunate patient with Alzheimer's disease. So the brain activity here is much lower. So we can also look at physiological reactions with this type of technology. But it can also be used to detect cancers and things like that, other types of lesions in the body as well. It's a modern, and we use more modern, so it's called positron emission tomography. And today, much activity is going into development of workable tracers. I come to this summary, a brief summary, and I'm going to read what I have been writing here. Radio tracer technology offers unique measuring possibilities for many industrial, medical, environmental, and civil engineering applications, and are in many cases the only viable alternatives to measure mass flow and study and optimizing processes where mass flow and chemical or biochemical reactions are essential. Future use of radio tracers at remote locations will have to apply short-lived radionuclides. And I would say not only at remote locations, we also nearby production machines like cyclotrons, reactors, and so on. We should strive to apply short-lived radionuclides. for instance, produced by radionuclide or radiotracer generators. Many such devices already exist, and several are still in the development phase, and it's very actively being developed now. So different tracing methods are it is a very much alive technology. And that was, in fact, what I was going to tell you today. About just maybe a very last comment is that this has been just, I picked some examples. I would call it pinpoint in the technology area of this technology. So there are many more to it, and much more to it. And but then, of course, one has to enroll in some course that that lecture the technology. Okay, good luck, and thank you for listening.
Thank you very much, Tor, for this presentation. It was very clear, and also the graphical representation was very useful to understand the process and the method flow. Okay, so now we have time for questions or comments. So I would like to invite the audience to open the microphone or write their question in the chat so that Professor Bjørnstad can answer.
Should I remove the presentation and go back to the main?
As you prefer.
Okay.
Professor Tor, this is Mario. Thank you for your interesting presentation.
Hello there.
I have a question.
Yeah.
As you know, usually when we teach radiochemist and we teach about radio tracers, some problem arise from parasitic effect that can absorb this low amount of tracers.
Yeah.
And so I'm curious about how this problem can be solved in tracer technology, because some situation must consider big volumes, big spaces, and when we use radio tracer, for example, we buy radio tracer with carrier, isotopic or non-isotopic carrier. And so my question is how this problem can be solved in radio tracer technology.
Well, you are pointing to a problem that still exists. You see, it's a very good question. In laboratory experiments, if we start there, we tend to use we have to avoid the radio tracer to absorb in glass walls, on glassware, and so on. That can partly be solved by saturating the glass wall beforehand with some similarly charged compounds. Then you can reduce the absorption. You can also reduce the absorption as a function of pH. At lower pHs, less absorption will take place in the glass walls. But in many cases, as you rightly said, we have to use carriers. And if possible, we can use elemental carrier. That is the best to use. But it can also be carriers from the same chemical group. If it's possible to impossible to use some very precious, let's say, carriers, then we can use something that is not so expensive. So that is the only thing I can sort of propose, that is to use carriers. And in open situations, like in reservoirs, open reservoirs, in water reservoirs and so on, there are, in many cases, there are natural carriers. For instance, in seawater, in oil reservoir, and also in geothermal reservoirs, there are natural carriers for some of the tracers we tend to use. And we select those tracers which has a natural carrier. For instance, a very interesting tracer in open reservoirs. It's not short-lived. I have tried to be an advocate for short-lived tracers here, but it's not so short-lived. It's 22 sodium. 22 sodium is a very nice radionuclide, 2.5 years half-life. And in any situation where we, let's say, inject seawater, there is a lot of sodium on beforehand, and
Yes.
that works as carrier for that tracer. So it moves as it should do. But of course, another thing is that in a rock, and especially in sandstone rock, it has a positive charge, and so there is absorption to the rock. So it is in a rock. It is not a passive water tracer. It is an active water tracer. We can use it to measure ion exchange capacity of the rock, because the tracer is a little bit delayed with respect to treated water, for instance. It was a long answer. I don't know if that was an answer to your question, but
thank you very much. It's a very wide answer, and thank you.
I would like to ask you, instead for the youngest that maybe there are connected now, many of the application you described were in the field of oil and gas industry, and so maybe in the field of the chemical engineers or something like this. But
Yeah.
maybe a simply chemical background is not enough to approach this application, or not. Maybe a much more multidisciplinary background is necessary in this case.
If you ask, do you ask? I'm not quite sure if I understand your question exactly. Can you try to?
Yeah. I'm thinking about which kind of background the youngest should have in order to approach this kind of activities.
Okay. So I see. No, pure chemistry is not sufficient. One has to have a background in handling or a certain competence in handling radioactive material. That means chemistry course, it means radiation safety course, and things like that. So, that's a minimum in order to be able to be allowed to do that at all. Of course, supervision in a laboratory, supervision from somebody that is experienced in this, okay, then you can start with some chemical knowledge and acquire knowledge about this as time goes on. In order to be able to apply, be allowed to apply this technology externally, you have to have this background.
And you have to take care about all the radioprotectionist aspects.
There has to be safety issues that you have to look at, and you see safety measures. You have to be prepared for things can happen. There can be a spill. You can be unlucky. You can crush an ampulla of a tracer and contaminate just right there. Although it's short-lived, but still it lives for some time. So, and you have to do the cleaning. You have to know how to do the cleaning. You have to know this kind of stuff, and you have to know how to detect the activity.
Also, because I think that accident can happen.
Accident can happen. We are never 100% sure of anything, and we have seen in large experiments in oil reservoirs experienced companies have done blunders. They have really yeah, and we have to be. We shouldn't fear it, and we should not. But we should be prepared for doing something if unfortunate things happen like this.
Yes, to manage the situation.
Yeah, we have to manage the situation. Be prepared to manage the situation.
Yeah, and to avoid problems for the workers, people, or maybe also for the environment.
Yeah, exactly.
Okay. Thank you very much for your time, for your availability for this webinar, and of course for all of you that are here.